which is fixed to a rigid support. Axle is frictionless. A string is wound and over here there is a point mass of small m which is hanging from here, and the system is released from rest. We are asked what is the angular velocity of this as a function of time, and we have to get the answer using angular impulse momentum equation, that is torque into dt is equal to dl. So we are constrained to get the answer using this equation itself. So if we look over here and try to find the angular momentum of this point O, first is let's understand the direction. The angular momentum of this omega is in this direction, so angular momentum of this is inwards into the plane of paper. By right hand thumb rule, it is into the plane of paper. This particle is moving in a straight line at any time. So we can also understand angular momentum as movement of momentum. So it means this is velocity is going to be in this direction. So this is line of momentum. So this is momentum. This is momentum. Moment of momentum is obviously this is once again in the downward direction. So once again this is momentum is in this direction, this the distance. So angular momentum of this, moment of momentum of this is in this direction only. R cross mv, that is R is this, mv is in this direction, that is mv parallel to this is same thing. Momentum is in this direction. This is smaller angle. So R cross mv, the momentum is in this direction only. So it means both the momentum B of this and B of this, they are into the plane of paper. Let's try to solve it. When you take torque about O, so whether the particle is here, here or fixed over here is one and same thing. So because this is a pulley, its center of mass lies on the axle itself. So because of its own weight, the torque of this weight is going to be equal to 0. So it is only rotating only because of this particle only. If this particle is not there, this will remain in its position. If this is stationary, this will remain stationary. If it is moving in the velocity, angular velocity, it will continue to move. So because the friction over here is equal to 0, there will not be any alpha. Because of this only there is some alpha, and this is going to have some acceleration, linear acceleration. So if we fix over here, the torque about this is going to be what? Mg. The force over here, what is acting is, that is mg force is acting over here. Mg into this R. So torque is mg into R. So mg into R is the torque of this force about this axis, and the direction is given by right hand thumb rule, that is in this direction it is minus k. So torque is equal to minus k cap mgr. So this is, we have the torque about the point O. So this is torque about the axis O. Let's come to angular momentum. Angular momentum of the system. This is obviously, this is a disk, we can easily find I omega is angular momentum. Otherwise also, that is if we say what we did earlier, let's say this is a particle which is moving in this direction. Mass m, velocity v, and let's say this is a distance r. Or then let's say this is the distance, let's say directly take perpendicular distance, this is r. So we say angular momentum is what? Angular momentum is moment of momentum, that is mv into r. This is this thing. V is also at this instant, we can also be replaced by V is equal to R omega. V is equal to R omega. So when we put over here, so that comes out to be mr omega into R, that comes out to be mr square omega. This is what? This is I of particle only about this axis. So once again it comes out to be I omega. So angular momentum I omega or R cross mv, one and same thing. So angular momentum of this disk about this axis is I omega plus angular momentum of this particle about this axis is moment of momentum mv into r. Both are there in the same direction, so we have simply added it. Had one been in the opposite direction, which we'll do in the questions to come, we'll do it. So we would have to subtract it. So over here I0 is mr squared by 2. About this we know this is of disk is mr squared by 2. So mr squared by 2 omega plus m, v is r omega, mr omega. So this comes out like this, mr square omega taken out, and vector notation it is going to be minus k cap. So we had found L0 also, that is angular momentum of this system at any time t. Initially when it was, the whole thing was released from rest, at that moment the angular momentum was 0 about this axis because there was no omega. So at time t we have this angular momentum. And what is the torque acting? This torque is acting over here. Now we can use the equation, that is torque into dt is equal to dl. Using that equation, so dl, that is change in delta change, that is change in angular momentum, is equal to angular momentum final minus angular momentum initial. Angular momentum initial is 0 only. So angular momentum final is this much. So delta L is this much. Now we are talking of this side. Torque is what? Mgr. dt integral 0 to t. Once it is released from rest, we intend to find what is omega as a function of time. So mgr dt, we integrate 0 to t, and from here we get omega as 2mgt over m plus 2m bracket closed capital R. So this way we can use the angular impulse momentum equation.